title of my talk is Soil Remote Sensing in the Era of the Fourth Industrial Revolution. I'm Eyal Ben Dor from the Department of Geography, Porter School of Environmental and Earth Science at Tel Aviv University. So, Klaus Schweppes in 2016 have sketched the industry, the industry line, and he started from the first industry in the 18th century and end up at today. And as you see, in every century and every revolution, you have something new that we all take for the life, for the comfort of life. Like in the first industry revolution, we have the mechanization. In the second, we have mass production. In the third, we have computer and automatization. In the fourth, we have cyber physics and system. But we can also sketch the industry number five, which is AI, IoT, deep learning, and this is something that is evolving every day. So the fourth and the fifth industry revolution is taking place at the same time. And I would like to talk today about how soil mapping have been started in the first industry and end up today, and what is the future of this revolution. First of all, let's speak about the definition. Soil is the upper layer of the earth. It's about 2 to meter deep, and it is actually represent the loose surface material which is dug, plowed, and being a medium for plant to grow. So this is most important thing to understand, that soil is something that is producing food. So it is actually the interchange between the atmosphere, hydrosphere, lithosphere, and biosphere, and this is the pedosphere. So this is the interface between all the spheres that we know and study today. Soil is not only for field quantity, but it is also for food quality. And as you see here, even this is actually taking from a Starbucks cafe in New York. So you see that each of the cafe taste is actually controlling by the soil. We know this very well from the wine quality. So soil is not only important for mass production, but it's important also for the quality of the food. Now let's define what is soil survey. This is taken from the Wikipedia. So soil survey or soil mapping is one of the very important activity in order to grow crops, and it's a process of classifying the soil type and other soil properties in a given area and geoencoding it to the information into a map. It applies the principle of soil science and draws heavily from geomorphology, theory, soil formation, physical geography, vegetation, and also soil chemistry. Um, So the practical way to map soil is actually to dig a trencher and to describe the profile of the soil. The profile is actually how the soil forming, and it shows how the soil is actually can be defined by orders, and then also can be assessed as a soil production uh, area. So you see that you take with you some material like Munsell color charge, and you describe the soil qualitatively in the field. Actually, the soil is not only the surface, it's also representing the profile. So as we said in the definition, it's about 2 meter depth. And as you see, we have profile, and the profile is actually telling us how the soil was forming and how is the soil now behaving for food production. So you take the soil to the laboratory after you define it qualitatively in the field. You take it to the laboratory, and by the laboratory you do lots of analysis. We know those analysis, the chemical, physical analysis, and then you take this information and put this information on top of air photo, and you produce the map, and the map goes to the farmer or to the end user, and the end user can actually plan what he is going to grow on his field and what he is going to do in the field in term of agriculture. Looking for the first industry, you see how they were sampling soil. This was a very primitive way, but also this is the way that people are doing today. They have digging the soil from the surface. They have this auger. And now in the industry number three, when we have the machinery, we can do it automatically by motors. And then we have to take information about the soil. So we have of course, the camera, and we have the film. The camera was actually evolved in 1833, and then after the film, and this was in era number one. Then we have to take the camera very high in order to take the soil picture, the area that we are going to map. So we first use a kayak, and then balloon, and also pigeon, and then after, in the very beginning of the last century, we use also aircrafts. We brought the information to the laboratory, and as you see, the lady is using the air photo, that is actually recorded on a film, and then she produced the soil map to the farmer. Now we had to go further, because in aircraft we can get very, very nice altitude, but not as much as we want if we would like to cover lots of areas. And this is industry number two, where the rocket has been invented. And of course, this is not a rocket with a camera, but it is shown that in 1926, it is possible to get higher level than the aircraft. Then after, later, it was able also to get into the space with camera, with film, and bring the film to the Earth. And this is the first photo of the Earth from space. And this is actually show that it is possible to get to the space with remote sensing sensors. And later, after, it was also used for military and for getting information from above. And this is the Corona satellite program of the US, which was a top secret at that time. In the mid of last century, they sent a satellite to the space with film, and then the film, as you see here, this was the film, and the film was in this capsula. And after the film was finished, the capsula went with the parachute, and this aircraft was actually collect the capsula and bring it to the laboratory and produce information or map information. This is the Pentagon, but as you understand, also information about soil, rock, and also forest. Until 1994, this information was top secret at the Pentagon, but then in the Clinton regime, he was free this information to public, and now everybody can use it. But this proved that we can get information for space and bring the information by the film down to Earth and get information that can be mapped for many, many purposes. This was, of course, for military applications. Now we have to go further and understand that what we all see at the time that we had this information is the vision of the eye. So we see only three colors, or maybe more than three colors, but three basic colors: red, green, and blue. And from this color, we can make composite of other colors. But if we take a look on this graph, and this graph showed us this is the electromagnetic spectrum, and this is how we can see in our naked eyes from very blue to the very red, and between those ages we don't see anymore. We are not sensitive, so we can plot this information on a reflectance curve. And actually, as you see, this is the very small information we can see. So let me highlight it. So this is the information we see, but the information also of the electromagnetic radiation of the earth and of course the soil is much higher. This is the information. We don't see this information. And the idea is how to get this information to our naked eyes, or how to get this information and have it mapped in order to provide very accurate map to the end user. So as we see, we have information of soil, we have information in grass and water, and they are totally different from each other. So this is very good because we can understand that information in this case, or information in this format, can provide us much more information as the naked eyes. Now let's go to the other invention. This is the spectrometer. The spectrometer is invented by Fraunhofer in 1880, and what he actually did is finding lines in the spectrum that we can see by our naked eyes, and these lines actually provide us information about the material. So each line provides us information about the chemistry of the material, and this is the spectrometer, the first assembly that observed color with chemical meanings. Later on, in the first century of in the very beginning of the last century, Einstein has discovered the photoelectric effect. This was in 1921. He got Nobel Prize on that, and the idea was that if the photon from the sun hit a metal arrangement, it can move the electron from one place to another, and this electron now can be actually move and get and provide or produce current, that this current can be measured. In 90 in 2009, these two gentlemen got the Nobel Prize about inventing the CCD, the charge coupled device. The charge coupled device is actually is developing a development of the photoelectric effect, where each of the points here, we don't see them, but we have here a matrix of points. Each of the points is a photoelectric point that provide us current, and this current can actually measured, and by measuring the current we can assume what was the photon energy and also the photon wavelength. The other, after we have this invention, then the first digital camera has been invented in 1997. And then after, it was an invention of the three CCD, three layer of the CCD. Each of the CCD is sensitive to each of the color, red, green, and blue. And once we have these three CCDs taking the same picture by the different sensitivity to the red, green, and blue, we can compose this information and get a color image of the object. Now, the second invention was to take the white light and disperse the white light, and each of the photons of the same of the different wavelength can be actually captured by a charge coupled device, or by the electrical by the charge coupled device that can provide electrical current, and this electrical current can be captured, and by providing the electrical current in this axis, and this is the wavelength that is based on each of the color of the rays. We can plot a graph that we showed before that we call it a spectrum. It's like the graph of Fraunhofer, but we can do it in much larger areas, and also we don't have to look by our naked eyes. We can archive this information, and afterwards we can analyze it. So this is the first spectrometer that did this kind of idea. It took information from the soil, and then after we took this information to the laboratory and analyzed the information. And as you see, we have very, very informative spectrum of the soil or the objects that we are looking at. So let's define what is soil spectrum now. It's a plot of reflectance part of the electromagnetic radiation that interact with the soil surface across the what we call visible, near infrared, short-wave infrared spectral region of the sun illumination. This is the white sun, white radiation that we can see only the red, green, and blue. So if we are putting this together, you have here the spectrometer. This is a model spectrometer. You have here the archive place and also the dispersion place. This is the four optics, and you have a fiber optic that connected the two assemblies. And here you look at it, and sometimes the reflections goes back, sometimes it goes on the front, but this is can be solved, and we know this information from many studies. And if we look on the spectrum, this is the spectrum that we get. So we use the sun, we collect the information, we see in our naked eyes only this region, and all other region is what we don't see in our naked eyes, but it is very, very informative zone of the interaction between the photon of the sun and the soil underneath. So we call it VIS. We call visible, near infrared. This is infrared, and this is the shortwave infrared. We actually define those regions as this definition. And if you go to the literature, this is how you find those radiation. So in all, we have, this is a scheme of a soil spectrum. What we have in the soil spectrum, we have many information. For instance, we have calcite, we have organic matter, clays, hydroscopic water, organic matter, and iron oxide. But we have much more than that, because each of these component, we call them chromophore. Each of these component is actually correlated to other properties of the soil. So I will show you later on how we can define many other soil properties that are not direct chromophore of the soil. So they are actually a fingerprint of the soil, and each soil has the same spectral feature, but two different soil, they don't have the same spectral features. So we can say that they are very, very nicely represent a fingerprint of the soil. So if we remember, we have the first spectrometer, then in 1974, then we have the second spectrometer. This was a spectrometer that actually built by NASA JPL, and this was much more commercially at that time. And if we go later, we have in 2000, we have a very nice spectrometer by this company. And then we have many, many other spectrometers that all provide soil spectral information. Today, all of these spectrometers are public available, and you can buy them relatively in relatively cost-effective price, and you can use them to define the soil spectral information. But what you do with this soil spectral information, you collect them. So these are soil samples, and all of these soil samples have been analyzed in the laboratory for wet analysis, for chemistry and physics of the soil, but also they were measured by spectrometer. So we have all here, we have a soil spectral library. This soil spectral library contains lots of soil from different regions of the world with different properties, and using this information, what we call deep learning, we can get in the end a calibration curve that can actually, if you measure other soil without knowing what is in the soil. For instance, this is a moisture. If you measure them by this equation or other equations, you can actually uh, predict the water, in this case, the gravimetric water of the soil, without bringing the soil to the library. And if we go further, we can have not only the multiple regression analysis, we have a lot of other analytical tools. So you have this soil spectral information. This is the archive. You have the model. You have the spectral measure bringing to the archive. Then you have the model, and this is the model that we have the calibration and validation. And then you can use it actually in the laboratory, in the field from, let's say, airborne, and also on top of tractor. So altogether, you can use this information without taking the soil to the laboratory and doing the analysis immediately in the field. This is just to show that you have the very nice calibration or very nice correlation between the carbonate, organic carbon or matter, specific surface area, cation exchange capacity, clay content, hygroscopic moisture. And you don't believe we have so many others that have been determined by other colleagues. And today I can say that the source spectral analysis is just providing floods for applications that we can use this information. One of the most important application is to use it in the lab, in the laboratory. So you see here the spectrometer, it is used in the laboratory, but not only for soil. Today, you can find this technology very good for food, textile, tobacco, pharmacological product, medicine, vegetation, and of course, soil and more. I would like to mention that in Industry 3, it was mentioned that the CCD was invented by those people that we showed earned the Nobel Prize in 2006. But if we are taking into account that this guy, Professor Alex Getz from University of Colorado at Boulder, he invented the PRS, the first spectrometer, by using this CCD. So he took this CCD. The CCD was for film, for images, and he took this CCD and he actually converted into the first spectrometer. Also, he took the CCD and also converted it to the image spectrometer. Image spectrometer, I will speak about in few minutes. What is image spectrometer? It is actually to look on the spectrum in spatial domain. So altogether, he was the inventor of these two things that today we are using them very much in many applications and many disciplines and field. So I would definitely say that this guy is one of the nominated for the Nobel Prize in 2000 something. So I hope he will get the Nobel Prize for his inventions, because today we are thankful for him for anything that he had invented in the last century. So I will speak about the image spectroscopy or spectral imaging. So what you see, this is this is a line of pixel that is actually also using acquiring by the CCD, and this line is actually providing for each of the pixel a spectrum. So if for instance, this airplane move to this direction, we have line and another line and another line, and then we sum up all of the line, we see the image. This is the image, and each of the pixel has a spectral information. So this is the color that shows spectral information. The red color shows high reflectance, and the blue color or the dark color show low reflectance. So we have a cube of information, and this cube of information can provide us information about the atmosphere if we are flying the airplane high above. Also about the lithosphere, this is the soil, about the hydrosphere, the biosphere, and also about the cryosphere. So today, spectral imaging is not only for soil, It's for all these spheres. And this is only thanks to Professor Alex Getz. So if we go to the Wikipedia, this is the definition of the image spectroscopy. So we call it also hyperspectral remote sensing. And I will just read to you what Professor Getz in 1994 defined it as a simultaneously acquisition of images in many registered spectrally high resolution continuous band at selected or all spectral domain across the UV, visible, near infrared, shortwave infrared, midwave infrared, and low wave infrared spectral region. This is the wavelength of the technology that covering today the camera that using for spectral imaging. And today you have many spectral imagers today, starting from the average, very big one, and ending today with this very small one. And this is also of head wall. It's a size of a golf ball. And also we have platforms that start from very heavy aircraft to drones. So today it is very easy to apply this technology. Now let's look on the computer or computing power from the era of number 3 to era number 4 today. So we start the hyperspectral remote sensing, or sorry, the spectral sensing as invented by Alex Getz, Professor Getz here, and we are here. So see how this is logarithmic scale. See how far we are in computing power today. So we started with very big computers and magnetic tape, and today we are archiving information in very small device, and we can fly the camera, the very small camera, light camera, on top of drone and not on very heavy aircraft. So if we look on the point spectroscopy and image spectroscopy, they are, of course, combining each other. We have here soil spectral library, and we have here information. We can conjunct this information and get information about geology, vegetation, water, and of course, soil. There is strong linkage between these two data acquisition. The other thing is, of course, to do deep learning, and this is the era 5, I call it. Deep learning is something that is evolving every day. You have many data, and this data is being analyzed by many mathematical, statistical approaches and modeling. And in the end, what you get the model that can be a spectral model that is actually applied to each of the pixel, and in the end you get a picture or image of the soil property. For instance, this is a soil property of organic carbon. All of the dark pixel are vegetation, so we could not actually detect the soil, but this is very informative information that is going to the farmer. And as you can see here, you see much more information to the farmer. We have the soil moisture, the soil salinity, soil spectral surface area, and the soil organic matter. And this goes to the farmer. Actually, these images are being made by, let's say, a couple of minutes of data acquisition. And if we have the model, it can be run in few seconds, and the farmer can have information about his field in a very rapid way. We can apply it also on top of tractor and get information of the area that is being cultivated. And for the future, and also we are now doing this in our laboratory, we can put the the uh, the model, the soil spectral model that, for instance, here is the clay, and fly it on drone and get the soil mapped in real-time mode for the farmer. So it could be actually sent back to the farmer, and without waiting for the drone to land and to get the information and process the information, as you have the model already in a chip here on top of the drone. So now the question is, we saw that we can do it in the field. We saw that we can do it from aircraft, either man on armman. But how about the satellite? And this is something very interesting to say. the space agencies understood today that soil is a very important pillar of the Earth, and as they were uh, very interested in many years about vegetation and rocks and water. Now they understand that soil is very important part of the globe, and now they are putting lots of effort in order to put hyperspectral or imaging spectrometer in space. And once we have this information from space, we can go all over the world and provide information to farmers on most on real time on or very close to real time information to the farmer once he provides us the coordinates of his field, and we don't have to lean on aircraft anymore or on drones or and this kind of information is being actually product of era number 5. And I would like to give you some uh, sketch or some information about the satellite hyperspectral satellite program. And as you see, we have lots of space agencies such as ESA, ASI, NASA, CNES, and also DLR, and the ISRO India. All of them are uh, planning to put satellite in space. Some of them already in space. For instance, the blue are in space already, and we are using them. You are using them very intensively to demonstrate that soil and spectroscopy of soil from space is possible, and it's very informative and will provide to the farmer very accurate and valuable data to farming the soil. So I would like to, as you see, this is the to conclude the talk and summarize it by saying that a journey from the industry number 1 to industry 5 has demonstrated a remarkable progress in the remote sensing of the earth in general and of the soil in particular. And the new spectral-based remote sensing era will contribute to the mankind more than we can imagine at the moment. So this is just to open your mind and say that we have technology, we have targets, but we still didn't fill all application of this technology and the targets, and the sky is the limit. I would like to thank you very much for your attention.